Hello students, we are on to the next lecture of alkenes and we have completed so far all the preparations of alkenes. I hope you have studied them well, and today I will be starting with chemical properties of alkenes. First, I am taking addition reaction, and in today's lecture I will be completing addition of hydrogen, halogen and hydrogen halide. Right? First, let me explain. Alkenes, we know they are those which are having double bond between them, between the carbon atoms. So when they have double bond between the carbon atoms, that means there is one sigma and one pi bond. One sigma and one pi bond. So pi electrons are readily available to the attacking reagent. When pi electrons are readily available to the attacking reagent, so any species which is in need of electron, that is electrophile, electron loving species, electrophile can attack the alkenes. So in a way we can say that alkenes undergo electrophilic addition reaction. They undergo electrophilic addition reaction. Actually, not only alkenes, all the hydrocarbons which have multiple bonds will undergo electrophilic addition reaction. Okay. So, first let's consider addition of hydrogen. Addition of hydrogen. So, this partly we have done, in alkane. In alkane preparation. Right. Suppose I take some alkene. Say I have taken ethene. If I have to add hydrogen, that is to be done in the presence of nickel, platinum, palladium, any one of the catalysts you can use. If you are using nickel, you will have to heat it. If you are using platinum, palladium, it can occur even at the room temperature. And it will result in the formation of saturated hydrocarbon. So, addition of hydrogen mein what happens is the unsaturated hydrocarbon gets converted into saturated hydrocarbon. If you want, you can take more number of carbon atom. Alkene, suppose I am taking say propene, you can add H2. Because there is only one pi bond, you will add one H2. Right? So, you will be using nickel, platinum, palladium. If it is nickel, you have to heat it. You will get 3 carbon alkane. That means you will get propane in this case. This is addition of hydrogen. And we have already done in the alkane preparation that the name of this reaction is Sabatier-Senderen's reaction. Senderen's reduction reaction. Okay. Now this was the first one. Now we are moving on to the second one, that is addition of halogen. Addition of halogen. There are various halogens, say fluorine, chlorine, bromine, iodine. When we are adding them, you can have the different reactivity. Yes. So if I consider fluorine, chlorine, bromine, iodine, which one will add on easily? Okay, the order of the reactivity of the halogens to the alkenes follows this order. Fluorine is most reactive. Iodine does not react with the alkenes at room temperature. It doesn't take the, at ordinary temperature, you can say iodine does not react with the alkenes at the ordinary temperature, whereas this is very easily reacting with the alkenes. It is too rapid to be controlled in the laboratory. Right? Normally when you are writing for alkene, we consider with chlorine. You can write with bromine also. That is not an issue. Normally we write down with reference to chlorine and bromine. Suppose I am considering here reaction with bromine. This is also a type of electrophilic addition reaction. That is there. All these are type of the electrophilic addition reactions. Now if you are adding bromine, first thing is the electrophile has to be generated here. So we use carbon tetrachloride because this bromine is non-polar molecule. It will not get polarized. So as to polarize it, the medium is required and it gets polarized and it will form Br+. That will start the reaction and this will be electrophilic addition reaction. This bond will break. Double bond will become single. One bromine here, another bromine here. You will get CH2, Br and CH2Br. That means you are getting vicinal dihalide. You are getting vicinal dihalide. This is a very, very important test because this test is used for, this particular reaction is used as a test for unsaturation. It is a test for unsaturation. Now what is a test for unsaturation? Bromine is reddish brown in color. It has color. It is reddish brown in color. So when bromine is added on to some unsaturated hydrocarbon, then its reddish brown color will disappear. Its reddish brown color will disappear. So you can use this as a test for unsaturation. Suppose you are asked a question, how will you distinguish between ethane and ethene? How will you distinguish between ethane and ethene? You will say bromine water test. You will use this bromine test because the reddish brown color of the bromine will disappear with alkene and there will be no reaction with alkane. Got it? So this was the addition of halogen. Moving on to the another addition reaction, addition of hydrogen halide. Hydrogen halide means we are mainly talking about HCl, HBr or HI. These are to be added to alkenes. Okay, let's consider this normal alkene. Say we have a carbon-carbon double bond. If some hydrogen halide, say HX, is to be added on, it will add on by trans addition. Trans addition means it will not form a cis product. Means H will add here and halogen will have this side. So in a way you will have like this. See, double bond you will break. Okay, so H will be adding here and the halogen you will write down like this. This is a normal one. Right? And if you are comparing the order of the reactivity is like this. HI is most reactive, then comes HBr and the least reactive is HCl. Of course it will be HF, but that will not be able to add on. This, if we are talking about only 3, HCl will be the least one. Because if you see, chlorine is smaller in size. This being smaller in size means the bond energy will be more. Bond length will be less. More energy is required to break this bond. Nearly 430 kilojoules. This is 360 kilojoules per mole. This is 300 kilojoules per mole. Okay, so least energy is required. Now, suppose I add on 2 carbon-carbon double bond. That is ethene. I am taking the simplest example of ethene and I want to add, say, HBr. So H will add here, Br will add here. Or H here, Br here. It is one and the same thing. That means you will get the same product in this ethene. But the problem comes only if you are taking some unsymmetrical alkene. Suppose I take this alkene. This is unsymmetrical alkene. Unsymmetrical alkene means the carbon-carbon double bond, if you see, either side you are not having same number. Okay, if you just see, there is no symmetry. This side you have one, this side no carbon atom. This is unsymmetrical alkene. If unsymmetrical alkene, we want to add, say, HBr. If we want to add HBr in this, then what product will be obtained? We can just see there are 2 possibilities. If H adds here, Br adds here, or H adds here, Br adds here. You might think this way. So if first option is there, then it will form CH3, CH2, CH2, Br. If the second option, then CH3, CH, CH3 and Br. Now we got a doubt. Wherever there is a doubt in organic chemistry, there is a rule. The rule here is Markovnikov's rule. It is Markovnikov's rule. Okay, Markovnikov's rule says that this will be the stable product. Now, according to this Markovnikov's rule, we say the negative part, whatever you are adding, the negative part adds on to the carbon atom carbon atom with less number of hydrogen atoms. Less number of hydrogen atoms. This is having less number of hydrogen atom. This was the case. Yes, it is. From here we started with the unsymmetrical alkenes. This is the unsymmetrical alkene. So this is the negative part. This is positive part. This is the negative part. This is positive. This is negative. The negative part will add on to that carbon atom which is having less number of hydrogen atoms. So that means this is the stable product, not this one. This is a minor one. We can say the first one is minor product and the second one is the major product. Okay, this is just, I told you in a way how to understand it. It is negative part will add on to the carbon atom having less number of hydrogen atoms. Right? Make sure if only HBr is given, you will follow Markovnikov's rule. If it is in the presence of peroxide, that I will take in a separate video, then it will follow anti-Markovnikov's addition. Okay? Now let me explain the mechanism. Now let's write here, say you have CH3, CH, double bond, CH2. This is unsymmetrical alkene. So what are we adding on? We are adding on HBr. It is having H plus and Br minus. In the first step, this H adds. This will add up. There are two possibilities. H can add on this carbon atom or H can add on this carbon atom. Let us first let us draw the structure where H is adding on to the first carbon. That means CH3. If this H adds here, it will become CH2. Double bond will go away because this H plus is coming. That pi bond will be taken by H plus and it will form a bond. So that means this will go to H plus. It will pull H plus from here and make a bond with it. And this will remain as such H2 and there will be a positive charge on the carbon atom. Or the second possibility is H adds on this one, this carbon atom. So if it adds on this carbon atom, it will be CH3. This will remain H and this will be H3 and now it will form this species. This is 1 degree carbocation. This one is 2 degree carbocation. These are carbocations or carbonium ions. This is 1 degree, this is 2 degree. Of 1 and 2 degree, 2 degree carbocation is more stable. We have discussed that earlier also. 2 degree is more stable because of hyperconjugation or inductive effect, you can say. Right? This is formed now. And in the next step, this Br minus will add on. The first step where only H has added on is a slow step. And now this will be attacked by Br minus. So Br minus will add here preferably because this is more stable one. So you will have CH3, CH, Br, CH3. This is the product form. That means if you write down with respect to the first one, it will be CH3, CH2, CH2, Br. That means it has formed 1 bromo propane, and in this case it has formed 2 bromo propane. So when unsymmetrical alkene, for example propene, is taken, 2 bromo propane is the stable product. This is a minor product. This one is the major product. This is the complete mechanism I have explained you for Markovnikov's rule. Okay. Now suppose you are given this example and you want to add here HBr. What should be the product? First thing, HBr, H here, Br here, or H here, Br here. I told you Markovnikov's rule. So Markovnikov means you should be adding H here and Br here. You will be getting the product where Br is at the second carbon atom. This is not the right answer. If you are thinking this way, it is not the right answer. Because here there is a catch. This is H3. Sorry. This is H3. Okay. Now what happens in this case? First thing I told you, H will add on. Let us write here, H has added. CH3, CH, CH3. You will have CH2. Sorry, this is CH only. You will have single bond and you will have CH3 because H has added on. You got a positive charge here. This is 2 degree carbocation. If 2 degree carbocation is formed and on just the next one, you find that there is a possibility that if one H migrates this side, that means if this H, this was the carbocation, carbon containing positive. So if there is one H left over on the adjacent carbon atom, and if this is able to shift here and able to form more stable carbocation, because if this H comes here, it is definitely going to form a tertiary carbocation. That means CH3, CH3. This becomes H2 because this H has gone here and it has formed a tertiary carbocation now. So secondary carbocation has converted itself into tertiary carbocation, which is more stable. So it will prefer undergoing hydride shift. This is 1,2 hydride shift. So hydride shift will occur in this case. So where H will come here and it will form like this. Now in the next step, the Br minus will add on and Br minus will add here at this carbon atom. So you will have the product as this will be CH2, this will be CH3, this is CH3, this is CH3, this is Br. You will think that previous example it was not hydride shift. This was different. If you see H added here, right? Even if this comes here, it is going to get converted into 1 degree carbocation, which is not required. So here by H shift, you are able to get a more stabler carbocation. Then this is possible. Then this one will be possible. Now let's take this example also. In this, suppose this is a major product. I hope this you have marked it. This is a major product. Here, first step, HBr has to add. H will have to add. So of course H will add here preferably. You write down first as per Markovnikov what should happen. CH3, 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 CH. You will add H to the carbon atom having more number of hydrogen, make a carbocation. This is a 2 degree carbocation. So according to us, we will write down Br here. Again, this is wrong. Because on the adjacent carbon atom, you are having a methyl radical. Not this methyl. Methyl, if it comes here, means it is not the terminal one cannot come. Okay. So if this methyl comes this side, methyl shift occurs, along with the bond only it will come. Because there is no electron here. So this has to come here, gets attached. Then it is capable of forming a tertiary carbocation. So 2 degree is getting converted into 3 degree. How 3 degree? You will have CH3, this CH3, this is CH, this is CH3, and here this H3 has come down and you got this carbocation. Now Br will add here. That will be the stable product. You will have CH3, CH3, CH, CH3, CH3, and Br. This is the major product. So these are the 2 important questions I have considered. One and this one, where you are adding HBr to such cases where on one side there is H hydride shift which can occur, or just adjacent to the carbon double bonds there is one methyl group which can shift here and make that into a 3 degree carbocation. Here you are having 2 degree getting converted to 3 degree carbocation. So this is more stable. Here also 2 degree was getting, because from the adjacent H can shift, in this methyl can shift. In this case H was shifting, in this case methyl is shifting. Finally 2 degree is getting converted to 3 degree. Here also 2 degree is getting converted to 3 degree. And wherever now the positive charge is there, on that carbon atom, halogen will come and get attached, and finally you will be getting more stabler product. Is this point clear? So because in the mechanism we saw that there is a carbocation formed. So if there is more stabler carbocation possible, then go for H shift or methyl shift, otherwise not required. Okay, that's all for the video. Please learn whatever mechanisms or whatever reactions I have completed in this video. Thank you.